So I want to thank Christian Bauer for agreeing to give this talk. So Christian Bauer was an undergraduate. He received his undergraduate education at Karlsruhe, Germany. Then he was awarded his PhD at the University of Toronto under Michael Luke. After graduating in 2000, he subsequently took a position at UC San Diego. Then he moved to Caltech as a McCone Senior Research Fellow, and then later joined LBNL, a theory group in 2005, as a divisional fellow. And in a very short period of time, became a senior staff scientist. And then went on to win Outstanding Junior Investigator. And then he was also in 2010 awarded the Early Career Award by the Department of Energy. And he also that same year was a recipient of the Presidential Early Career Award. Christian Bauer is currently the head of the LBNL theory group. And by the way, for those who don't know this, but LBNL is another national lab in the United States. So that's one of the reason I invited him is I've taken a keen interest in his past work on a Monte Carlo simulation tool called Geneva, and that's a very that uses something called soft collinear effective theory. So I think some of my students might find that interesting. But he's also taken up quantum computing, and that's what he's going to be talking about today is quantum computing. And I'm very excited about the talk. So take it, Christian.
Sorry, I was still muted. Thanks so much, Terence. It's a great pleasure to be here and tell you about this work that I've been doing in collaboration with Ben Nachman, who's a staff scientist at LBNL, and Murat Freitzis, who is a former student at LBL and is actually postdoc at Rutgers at the moment, but he's spending his COVID times in Berkeley. So he's actually physically in Berkeley at the moment. Yeah, so I want to tell you some recent work of ours on quantum computing and quantum computer for collider physics, and I'll actually touch on effective field theories and soft collinear effective field theories in this talk. So I hope you find it interesting. And please, I will watch a little bit the chat and the raised hands, but if you have any questions, just interrupt, just speak up and ask any questions. Okay, let me go to the, yes. So, as we all know, one of the, driving quests of high energy physics is to, to understand the fundamental interactions that govern the laws of nature. And at the moment we have the standard model, and every measurement that we've done so far fits very well into the standard model, which has 6 quarks, 6 leptons, force carrier particles, photon, gluon, W and Z boson, and of course the crowning achievement, the discovery of the Higgs boson, which gives mass to all elementary particles in 2012 by the Large Hadron Collider in Geneva. And of course I should say, given some of the excitement that's happening, there are some experiments that sort of seem to show some deviations to the standard model, in particular the G-2 experiment that you've probably heard about. And I think there it's going to be very interesting to see, is it, do we really trust the uncertainties of both the theoretical and experimental uncertainty? Is this really maybe a first hint at something of a breakdown of the standard model, or maybe just an underestimate of theory uncertainty? So that's certainly really exciting. But really, what I kind of want to focus on and motivate in this talk to go about really how do we actually validate that the standard model is truly correct, and in particular, how can we use a machine, a collider like the Large Hadron Collider that you see here in this picture, to directly test the standard models. How do we compare the measurements performed at the Large Hadron Collider against our predictions from the standard model? And so what that really means. I need to be able to find a way, excuse me, to take the Lagrangian of the standard model. And then you can, if the most compact form, you can fit it on a coffee mug, but go from this Lagrangian and then essentially directly compare two experiments that are actually seen at a Large Hadron Collider, for example, here, sort of an event display from the Atlas experiment. And so what you really want to do is you want to go from the Lagrangian to completely fully exclusive events that has sort of hadrons in the final state. And you have to remember there's like typically, even though it doesn't look like on this event display, but typically there's hundreds of particles that flying out. And this is not a very easy task to go directly from this Lagrangian to sort of these predictions. So this is what I call one of the holy grails of high energy physics, is really truly the full simulation of a scattering process at a collider. So I want to sort of take a scattering process at a collider and directly take that and do the hard scattering that happens here, but then the subsequent emissions of other particles, gluons, photons, other particles, and then later the hadronization of those particles, and then compare the distribution of these final state particles with what I actually see at an experiment like Atlas or CMS. And so the dream, therefore, we've all learned, and hopefully, well, if there's undergraduates on this call, you probably have not necessarily learned this in detail, but essentially the formalism that we use to describe a process like this that takes me from some initial state, which in the case of the Large Hadron Collider is two protons that move towards each other, to some final state X, which contains these hundreds of particles that I want to measure, is via something that is called the S matrix. So what the S matrix is essentially is a state in the far past that is, in this example, two protons that move towards each other. And then I perform time evolution based on this Hamiltonian. And then I want to see what is the probability of getting from this initial state to this final state using the time evolution, which is governed by the Lagrangian of the standard model. So I create an initial state with two protons at some infinitely past time. I perform the time evolution with the standard model Hamiltonian, and then I perform a measurement of the final state X at the time t. And then I want to check, is the probability of finding a particular final state X consistent with the probability, the frequency with which I see that same final state at the LHC, right? If I could really do this calculation, then I could directly compare theory. Essentially, the only free ingredient in this thing is the Hamiltonian of the standard model. So everything in here is fixed. And so I can directly test whether the standard model Hamiltonian reproduces the data. So a couple of comments here. So this clearly requires quantum physics because everything in here is described by quantum field theory. So the Hamiltonian is described by quantum field theory. And as will become clear in this talk, this is not even remotely feasible using any computational resources we have available at the moment. We have essentially no formalism to really do this calculation at all. So we typically do an S matrix like this by using perturbation theory, and that typically allows me only to access a very small set of final states and with very limited number of particles in the final state. And I would argue that if we could really do this from first principle, it would completely revolutionize how we can compare experimental collider measurements with theoretical predictions. So this is where I'm going with this talk. So I first want to tell you how in principle I can set up a calculation like this by discretizing space. And I'll talk about this, and I could calculate this S matrix on a lattice. So instead of looking, having a continuous position, I sort of only look at discrete positions in space. But then I'll show you that this is completely, so that at least allows me to write the problem in a way that is tractable by a computer. But I'll show you that this is completely intractable on just even remotely possible to do a calculation like this. And then I want to show you that actually you can make this problem a lot simpler by trying to separate the low and high energy physics from one another, because as I'll argue, it is physics at the low scales that is really the hard part to compute, not the physics at the high scales. And I will show you that the problem will become a lot simpler if I do this. However, it's still completely intractable in any classical computer. And that will bring me then in my last part of my talk to computations on a quantum computer, where at least, not at the moment, but hopefully in some time, maybe in the next 50 years or something, calculations like this might actually become tractable to perform. Okay, first, can you guys hear me well, or does the microphone work well, or should I use my headphones? Does this work well?
It works, yes.
Okay, very good. Good. So let me start with a calculation of an S matrix on a lattice. So here's the slide, or this expression that I had before. And I want to compute this object, and every element that I have in here, in this matrix element, is essentially all expressions here are written in terms of fields, of quantum fields. For example, let's call them phi of x, but these are not necessarily scalar fields. This could be fermions, bosons, gauge bosons, and so on. But the important thing here is that so I need a field at every point in space, and position is a continuous variable. And actually, the field itself is a function of at each space point x, and that is also a continuous function. So this is a doubly continuous problem, and that's of course what quantum field theories actually are. And what you can show, and I'll go through this in a little bit in the next few slides, that if I discretize the position by essentially, instead of looking at all points in space, but I'm only looking at things on a lattice, on a discrete lattice, and then simultaneously also digitizing the field value phi. So instead of looking at a completely continuous, all possible values of phi, I'm sort of digitizing this. Actually, if you think about it, every computer that I'm using actually doesn't use a continuous set of numbers. It always uses a digitized version of it. It's just we're using typically nowadays 64-bit digitization, and that is very close to continuous. But in any ways, if I discretize both x and phi, then I'm actually turning this continuous problem into a discrete problem, and it turns into a quantum mechanics problem, which in principle I can simulate on a computer. And I'll show you how to do this. So essentially, evolution, any operator becomes a matrix, and essentially the whole problem here becomes matrix multiplication, if you want. So let's go through this a little bit and set us a little bit notation. So imagine I have here a space. I'm drawing it in 2 dimensions, but of course, real space is 3-dimensional. But so imagine I have my 2-dimensional space that fits on the slide. But instead of looking at every point on the slide, I'm only looking at discrete points, namely those points that sit at these black dots. Okay, and then I will try to essentially make this lattice spacing smaller and smaller and smaller, and then sort of take the continuum limit. So the closer I make this lattice spacing, which I call little l, the closer I approximate the continuum space time. And then second of all, there's another variable here, which is the length, the entire size of my lattice that I call capital L. And of course, I also want to take the limit L goes to infinity in order to simulate all of space. Okay, so the limit I want to take at the end is L goes to 0, little l goes to 0, capital L goes to infinity. But of course, there's there's a relation between little l and big L, namely capital L is the number of sites per direction times the distance between sites. Finally, I will put at each lattice point, I put a field phi. And as I said, I will digitize this. So I will not give it, will not make this a continuous function, but I only digitize this by giving you a certain number of values here at each lattice point. So now you can work out very quickly what the size of this Hilbert space is. So there's 3 variables that quantify the system. There's n phi, which is the number of digitized field values. There's capital L, there's NL, which is the number of lattice points per dimension. Okay, it's in 1 dimension, which is I call capital N here. And then there's of course the number of dimensions, which is typically 3. And so if you work out what the size of the Hilbert space is, it's n phi, the number of field values per lattice point, raised to the power of the number of lattice points that I have. And the number of lattice points that I have is the number of points per dimension raised to the power of the dimension. So it's n phi to the n to the power of d. Okay, but the point is it's a finite Hilbert space. So the entire problem is now matrix multiplication, where the size of the matrix is given by this number. So, and I'm not going to go over exactly how lattice field theory works, but essentially what you're doing if you encounter an expression in a Lagrangian or Hamiltonian that looks like an integral over some field value, you replace that on a lattice by a sum of the field values multiplied by the lattice spacing, right? So that's the standard discretization of an integral. I can do Fourier transforms like this, and becomes a very similar expression here, but I'm summing now over all lattice points weighted by sort of this exponential factor. I can also go back and forth between states on my position space lattice and actually transform to what is known as a conjugate lattice by taking a Fourier transform. Not really that important for this talk. But then another important thing, you always encounter derivatives of fields in my Hamiltonians and Lagrangians. And we all know how to discretize derivatives. It's essentially by taking the differences of, the first derivative is the difference between two nearby fields divided by the distance between them. And I can also do a second derivative. I just need 3 points to get a curvature. Okay, so the point is you can take any expression in your field theory, your continuous quantum field theory, and discretize it and put it on a lattice using expressions such as this. And states in my theory now just become vectors in this Hilbert space. So some state that has a certain wave function, which I usually write always in this form, it's some wave function phi of k. For each momentum point k, I can now write essentially again as sums over the lattice points and the field values in each lattice point, and then given essentially just a coefficient of this. Okay. So you can write the states like this, and then operators. For example, the Hamiltonian now becomes matrices in Hilbert space, right? So for example, the Hamiltonian of a scalar field theory is like d mu phi squared of a massless field theory. Then you write the d mu phi squared as phi dot squared minus grad phi squared, and then the phi dot squared becomes integrated over x. That becomes the sum over all the phi dot squareds at each lattice point, and then that discretized second derivative for the grad squared operator, which I gave you here. Okay. So the point here is that you can write everything in your Hamiltonian, everything in that S matrix, you can write in terms of either vectors in the Hilbert space or matrices in the Hilbert space. And then once you're done, that means all you have to do is matrix multiplication. So that sounds easy, right? Computers certainly know how to do matrix multiplication, but let's see how big the matrices actually are. Before I do that, very quickly, how you would actually do this problem. So you create an initial state vector at sometime minus t that correspond to two proton wave packets that move towards each other. Then you compute the matrix of the Hamiltonian. You need to exponentiate that matrix to get the evolution operator. But of course, you can use standard formulas for exponentiating a matrix. And then you evolve with this matrix. And then you get a new state, you get a new state out, and then you measure the overlap of this state that you get, which is obtained by matrix multiplication on the initial state. And then you measure another particular final state out, and you just compute the probability. Okay, so that sounds really easy. So why did I say that this is essentially impossible to do? Well, let's actually see what the Hilbert space is. So there's one important thing that I have to go over. Namely that the energy range, so you might ask, if I create a lattice, what are my constraints? What system can I actually simulate on a lattice? And if you think about this a little bit, if I have a lattice with a certain lattice spacing, you can imagine that if I have fields that have a wavelength that is shorter than my lattice spacing, so I cannot resolve that on my lattice. So in other words, I cannot distinguish a field that it's 5 wiggles between one lattice spacing or 10 wiggles between one lattice spacing, because I have no resolution on the space in between these lattice spacing. And so if you actually work this out, that tells you that at some point the highest energy state or the shortest wavelength state that you can hope to simulate on a lattice is given by the inverse lattice spacing. Okay, so the largest energy you can simulate on a lattice is given by the inverse, so 1 over the lattice spacing. And conversely, the smallest energy I can hope to simulate is I need to make sure that it sort of varies on the scale of my lattice. My wavelength is way larger than my lattice, then essentially I can't resolve anything, because then essentially the wavelength is constant over my entire lattice and I can't see anything. So that really means that the energy is bounded from below by the size of my lattice, and from above, well, it's the inverse size of my lattice, and from above by the inverse lattice space. Okay, so now you can say, well, let's see what energy range am I trying to simulate. And I told you earlier, I want to simulate the entire LHC. Okay, so 7 TeV is the energy of the Large Hadron Collider, and let's say we're okay to only go down to 100 MeV. I think that is actually not quite true, because that's sort of where hadronization sets in. So you probably want to go lower than this even. But let's say we're good enough to simulate from 100 MeV to 7 TeV. Now, if you plug these numbers in here, what do you actually find out? That this means, so you can directly solve this, right? N is given by the ratio of the largest energy to the lowest energy. So that means you need 70,000 lattice sites per dimension. So now you raise this to the 3rd power, because of 3-dimensional space. So that means you have 10 to the 14 lattice sites. Okay, that's a big number. So now, but remember, I also told you at each point, at each lattice site, I need to put a field in there, which I need to digitize. So let's actually remember, we are used to sort of 32-bit digitization, but let's assume, and I'll make that argument, you can make that argument that actually, if you just sort of want the lowest occupation numbers, you can actually get away with a pretty coarse digitization. So let's say we live with a 5-bit digitization. So 5-bit digitization means that the number of numbers I can actually encode in 5 bits is 32 values. Okay, so n phi is 32. So now let's plug this into the formula that I had, and that means that the dimension of my Hilbert space is 32 raised to the power 10 to the 14. Okay, so this is not 32 times 10 to the 14. That's a really big number, but 32 to the power of 10 to the 14. So for all intents and purposes, that's infinity. Okay, that's in a number that is so ridiculously large. And so clearly I cannot do matrix multiplication, multiply 2 matrices where each matrix is of size 32 raised to the power of 10 to the 14. Okay, so this is why I said it's completely impossible to do this calculation. And this is why essentially nobody has actually tried to do this. Okay, so what I will now do in the rest of the talk, I will try to do 2 things. First, I will try to work on this number. See if I can get this number down, because that is really what killed me, right? That made this 10 to the 14. So let's see if we can get this number down. And then see in the 3rd part of my talk if quantum computers can help to get a number down as well. Okay, let me pause here for a second and see if there's any questions regarding what I said so far. Okay, if not, let me keep going and talk about the separation of high and low scales. And as you'll see, this will help me to address this number here and make this number small. So let's look a little bit again at what is a typical event at the Large Hadron Collider. And the point I'm trying to make here, that involves very different energy scales. And for those of you who haven't really done that much or are not that knowledgeable in particle physics, I will give you a nice example also where sort of the separation of large and small scales, where you can see that in an example that you've all seen in the past. But anyways, so really what happens at a Large Hadron Collider, there's really sort of, I would say, 3 typical scales in the problem. There is the scale where actually my hard interaction happens. So I'm colliding 2 protons and I'm having really violent interaction where the 2 quarks, let's say, or 2 gluons out of the proton collide. and they have a huge momentum transfer, and they actually go in a different direction. Or this is where I produce heavy particles and so on. Okay, so this is and this happens at very, very short distances. So for example, this could be a collision of two quarks by the exchange of a gluon, say producing two top quarks. That's a typical example I'd like to study. So then at these short distances, now if these things separate further out, what then happens? Each of these four particles can now radiate additional particles off, additional gluons. Maybe I can have a decay, say of a top quark to bottom quark and a W boson, and so on. So these happen typically at medium distances, and I'll quantify this in a second. And this scale, at this scale, there is, there's not just a few of these interactions, but there could be many emissions that happen. And then finally, what happens is I can also radiate really soft radiation that happens sort of at even longer distances. And then, of course, I can hadronize the quarks and gluons that come out of these events and turn them into hadrons. And that is really happening at the longest distances, which are given of order sort of the size of the proton, essentially an inverse Fermi. What is important at a collider, in a collider environment, that really these three scales directly correspond to sort of three types of physical processes. There is sort of this hard interaction that happens that really is sort of this hard interaction, which happens at the scale, I call it Q, and that is really sort of the scale, the center of mass scale of my collision. It's not actually always 7 TeV, because as you remember, 7 TeV is the energy stored in the protons. But actually, it's typically constituents of the protons that collide with one another, and typically they collide at actually substantially lower energies. But these scales, what we're interested in is sort of scales of, maybe a TeV, maybe 1 TeV, maybe not the full 7 TeV. And then this radiation, this parton showering, that happens typically through collinear radiation. So essentially, I now have maybe two quarks flying off, two top quarks flying off in sort of back to back in my collider, and they can radiate other particles off. And what you can see from QCD, they like to radiate gluons off in the same direction, and as the direction in which these quarks are moving, and that's what I call collinear radiation. So they tend to go in the same direction, and that's how we form jets in a collider environment. And typically these, and so the typical scale here is the invariant mass of a jet, which are typically much lower than the center of mass, than the energy of a jet. Okay, so let me call this scale J. And then finally, I mentioned that there's soft radiation that can happen, and that soft radiation can actually talk to the different directions, the different jets. And you can show that the typical scale here is given by the geometric mean, the collinear is the geometric mean of these two scales. So the soft scale is the jet scale squared divided by Q. And so if Mj is much less than Q, then I have a wide separation of these scales. So Mj squared over Q is much less than Mj, which is much less than Q. Okay, and as I will argue, is this scale separation can really be used to understand the physics better. So let's try to see why having a separation of scales makes a problem easier. And this is where I promised to come to an example that probably all of you have seen before. And this is, imagine I have a charge distribution. So here I have a charge distribution. I think there is like 7 red charges, call this positive charges, or doesn't matter, and 6 blue charges, make them negative charges. And let's say I'm trying to understand what does the electric field look like, some distance r away from this charge distribution. Let's say this charge distribution is size L. Okay, so I can use some numerical computer code to solve this problem, and this is what the electric field looks like outside of this charge distribution. And maybe some of you have done some of these calculations following Jackson. And you probably know that this is a very complicated calculation to do. But you probably also know that if I actually go further out and look at this charge distribution much further away from the size of this charge distribution, then the problem starts to look a lot simpler, right? Because what happens at some point, this complicated physics here becomes much simpler, and when viewed from really far away, the electric field is essentially just radial field lines going out. And the reason is, of course, that viewed from really far away, I essentially don't resolve the details of this charge distribution any longer. I just see this as a point charge, as having a single positive charge. And then, if you work this through a little bit more, you can include corrections to this. Namely, you can sort of include the effects of the extension of this charge distribution by putting in a dipole moment, a quadrupole moment, and so on. And you can actually then really solve for the field lines out here in an expansion in the distance L over R. And in particular, the potential you can now write as, if I just put the charge in here, which is Q, it just behaves like a 1 over R potential. If I have a dipole moment, it behaves like P dot X over R cubed, and so on. So there's now short distance physics that describes what the charge distribution looks like. It's given by the charge, by the dipole moment, the quadrupole moment, and then by long distance physics that describes how the electric field reacts to these short distance quantities. And this is something that we use all the time in electrostatic. Okay, so this is the simplest example that I know of the separation of long and short distance physics. And of course, this is really powerful. For example, new symmetries emerge, right? If I look at the lowest order result, a rotational symmetry emerges in here, right? This because it just depends on the radius. There's actual a full rotational symmetry in the problem, which I can exploit to make results a lot simpler. And that is essentially what we're trying to do when we do effective field theories. So we're trying to exploit the same thing. We're trying to say, well, let's throw away all the short distance physics I can't resolve and only focus on the physics that I can resolve. And that's essentially, so in other words, you keep the total charge and you throw away the dipole moment, the quadrupole moment. But because it's an effective field theory, you can systematically include those directions. So as I alluded to before already, if you try to set up an effective field theory for collider physics, what you'll find there is sort of at long distances, there's 2 degrees of freedom that matter. You can either have particles that are collinear to a jet, that move in the same direction as a jet, and they're very energetic. Let me call these particles collinear. Or I can have soft particles that can go anywhere, that have energies much smaller than the jet, and they are soft. And you can really show that these 2 degrees of freedom, if I make that approximation, that reproduces QCD in the limit where Q becomes very, very large. And that effective theory is called soft collinear effective field theory. We worked that out now more than 20 years ago. This is a real field theory. It's an effective field theory, so you can make this completely formal. You can define fields for each of these different degrees of freedom. So I can define a field for the collinear directions for each of the jet. I can define a field for my soft particles. I can define how the momentous scale, how the field scale. That means I can do an expansion in derivatives according to what powers of how they pull down. So I can really systematically expand this theory. And in a similar way as in that charge distribution, things simplify dramatically if you do this. SCT has now been used in a really wide variety of physics, from formal understanding of QCD to flavor physics to jet quenching and heavy ion collisions, parton showers, Quirkonia physics, and proofs of factorization. And this is what I'm going to use for the purpose of this talk. So what I will show you, or I'm not showing you, I'll just state it, that if SCT allows you to simplify and write sort of cross sections at the Large Hadron Collider in terms of simpler objects that I can individually calculate. And in particular, a typical cross section at the Large Hadron Collider, or any collider, I can simplify using soft collinear effective theory. So this is an observable that says I'm having a certain number of jets. Each jet has energy much smaller than the typical energy of these jets, plus additional soft particles. So if I'm in an environment like this, which is essentially all observables that I care about at the Hadron Collider, then I can write this cross-section in terms of a hard function, which describes that short distance interaction. I can write in terms of a jet function, which describes that collinear, that radiation of particles, energetic particles in the same direction, which is formed out of these collinear fields in my Lagrangian, in soft collinear effective theory, and a soft function that is formed out of these soft fields. All of these objects, so this one is what is called a matching calculation. I can compute this order by order perturbation theory. And all of these objects, these jet function, the soft function, are really an operator definition in terms of fields in my effective field theory. Okay, so the point is, if I can compute these objects, these J1 to Jn and the soft function S, then I can combine them together with this hard function to actually compute any observable that I want at say, the LHC. And now what is important here, that these functions live at these scales that I earlier mentioned. So remember, I said the soft physics live at a scale that is the jet squared, the mass of a jet squared divided by Q. So let's say I have jets with energy 1 TeV, but they only have 100 GeV mass. Then the typical scale in the soft physics is given by 10 GeV. Okay. And now comes, and this is now where the argument comes. So if I just want to compute this soft function, which is still an object in quantum field theory, it's kind of, in principle, as complicated as an S matrix as I want. But now I can use the same tricks that I used on the S matrix to again go on a lattice, discretize, turn this whole quantum field theory problem of this S, and turn that into a quantum mechanics problem using the same tricks that we just did previously. But the important thing, I only need to go up to energies of order 10 GeV instead of the 7 TeV that I needed earlier. So that means that if I now want a lattice that is capable, or a system that is capable of describing just the soft physics, then I want to describe physics that goes from 100 MeV to 10 GeV. So instead of using 70,000 lattice points per dimension, I can get away with about 100 lattice points per dimension. Okay, now that is a huge improvement. 70,000 to 100 is a lot smaller. In particular, by qubit, I get 10 to the 6 lattice sites. Now, that's still 1 million lattice sites. It's still quite a lot, but of course, it's a lot less than 10 to the 14 lattice sites. Okay, so let's see what we've gained. So I think I made a remarkable improvement here. I went from 10 to the 14 to 10 to the 6. That's 8 orders of magnitude. However, unfortunately, the Hilbert space is still 32 raised to the power of 1 million. That's unfortunately still essentially infinity. Okay, that's still a humongous number. While it's way smaller than 32 raised to the power of 10 to the 14, it's still not something I can hope to simulate using matrix multiplication. Okay, so the point here is I've simplified the problem a lot, but I didn't go nearly anywhere where I can now put this onto my laptop or even a supercomputer and hope to do this matrix multiplication. And this is what brings me to the last part of my talk, namely whether I can do this actually on a quantum computer. Okay, so now I'm going to argue that I want to do this calculation on a quantum computer. And let me set the stage a little bit, because probably most of you have not actually worked on quantum computation. You've maybe read some popular articles, maybe you've had some course in your studies. But let me give you sort of 3 or 4 slide primer on it. So every state on a quantum computer is represented by qubits. There's a B missing here. So for example, I could represent, let's say I have 2 types of fermions. I can represent one type of fermion as a state 0 and a state 1. So what you should imagine here is that there's a system. So think of this as the ground state. Think of, the easiest way to picture a quantum computer is sort of a 2-level system, quantum mechanics system, and 0 is the ground state of that system, and 1 is that excited state of the system. And if I have multiple qubits, so 1 qubit is essentially 1 atom that can either be in the ground or the excited state. And if I have a quantum computer, multiple qubits, there will be a multiple of these atoms next to each other. Now I can represent true or false, again, as 0 or 1. And I can even represent, say, numbers, like say 5, in the normal binary notation. I can actually say the number 5 means that the first qubit is in the excited state, the second qubit is in the ground state, and the third qubit is in the excited state. Then that reads as 1, 0, 1, which is the binary representation of the number 5. Now I can operate on these states using unitary operations. So for example, if I operate on a single qubit, that is the space, the Hilbert space is 2-dimensional, it can be 0 or 1. So that means any operation on a single qubit is governed by a 2-by-2 matrix. And for example, if I operate on a state that has 2 qubits, that is given by a 4-by-4 matrix, because there's 4 possible states in a state that has, I can have 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 states I can have in a 2-qubit system. And another important thing is that all unitary operations can be built out of a very small set of basic operations. In particular, they can be built out of single qubit gates, so these 2-by-2 matrices, which, as you know, can be essentially built out of Pauli matrices. And one extra ingredient, which is these controlled operations, that essentially says if 1 qubit, so this notation here means I perform a 2-by-2, a transformation on this qubit down here with a unitary operator U, if the top qubit is at the state 0. And if I show a circuit diagram that has a solid circle here, that means I'm performing a unitary operation on this qubit here if the top qubit is in a state of 1. So I can write it as a tensor product of U cross 1, 1. Okay, and essentially you can build everything out of these types of gates. So let me give you a couple of examples. And the important thing, what a quantum computer can do, and then I'll show you on this slide here, is that it can perform many computations at once. So imagine I have a circuit that looks like this. So I have 3 qubits, I have 4 qubits in total. And I do some controlled rotation on this last qubit. And I do this in the following way. If this qubit is in a 1 state, I rotate this qubit, perform the operation U. If this qubit is in the 1 state, I perform the operation U squared. And of course, if this is 0, I don't do anything on this. And if this is 0, I don't do anything here. And if this qubit is in the state 1, I do the rotation to the 4th power. Now, what this operation does, if you think about it, if you think binary essentially, then if I represent these 3 qubits by an integer, so in a binary representation, right? So 3 bits can represent any integer from 0 to 7. Then I do essentially I rotate this qubit by a power which is the integer value in this. So U raised to the power, that should be I. So let me give an example. Imagine all qubits here are in the 1 state, in the 0 state. Then I'm not doing anything here. I'm not doing anything here. I'm not doing anything here. So I'm not actually rotating anything. So I'm doing the rotation U raised to the 0th power, which is the identity matrix. Now imagine all qubits are in the 1 state, then I'm rotating first once, then 2 more times, and then 4 more times. So I'm actually doing the rotation 7 times in total. But of course, the binary number 111 is the number 7 in binary notation, right? So if that means if the state is in the state 7, then I'm doing the rotation 7 times. So I'm doing U to the 7. The important thing here is that I can actually perform all 8 calculations at once, namely with only 3 gates. So if I put my initial state in a superposition of all integer states, of all possible 8 states, then if I apply the circuit, I'm getting a state out that for each I have the state raised to the ith power. Again, my typo here. Okay, so I've actually done the calculation U to the 0, U to the 1, U to the 2, all the way up to U to the 7, all in one shot, using only 3 gates. Now, of course, at the end of the day, I'm going to measure the state out. And if I'm not careful, I'm going to collapse this wave function. I'm going to pick out one of these integer states here. And then, of course, I'm only getting 1 answer out of these 8. And I'm not actually getting, I'm not getting any benefit from doing these 8 calculations at once. So the important thing on all quantum computing is how to use this parallelism carefully. So I thought it's instructive to actually go through one circuit and actually work this through a little bit in detail. So you get a little bit of feeling what circuit diagrams actually look like. It's nothing to do with my talk, but I think it's kind of cute. So, so I'm having here a 5-qubit register, so 5 qubits, and I've labeled 3 of these qubits by Q, 2 of the qubits by W, and these are really what I call my physical qubits, where I do something on, and this is sort of additional qubits that I don't actually care about so much. They're called ancillary qubits. And now let me write my state in the following form. So let me write as a tensor product of the W states and the Q states, and let me write it as W2, W1, and then the states Q3, Q2, Q1. Okay, and let's see what this operation does. Let's say I start my state in W1 and W2, both in the 0 state and the ground state, and my Q3 qubit in the ground state, and Q2 and Q1 in the excited state. Okay, so what this operation does, X, it's a flip operator, it's an AND operator. So what this says, you flip the value of the Q1 state. So my Q1 state is right now in the excited state. So if I flip it, I put it back down into the ground state. So after this operation, I'm getting to this point. Okay, so the last qubit here was flipped from 1 to 0. Now what this operation says, if the qubit Q1 is in the 1 state, then flip this the qubit W2. So let's look quickly. Well, Q1 is not in the 1 state, it's in the 0 state. So this operation doesn't do anything. This operation says if W1 is in a 0 state, then flip Q2. So W2 is actually in a 0 state. So let's flip Q2. So I'm flipping that 1 to a 0. Now the next thing says if Q2 is in a 1 state and W1 is in a 0 state, then flip W2. Well, Q2 is not in a 1 state, so this state doesn't do anything. This state says if W2 is in a 0 state, flip Q3. Well, W2 is in a 0 state, so let me flip Q3. Okay, and then this says if Q2 is in a 1 state and W1 is in a 0 state, flip W2. Well, Q2 is in a 0 state, so this state doesn't do anything. And this thing says if Q1 is in a 1 state, flip W1. Well, W1 is not in a 1 state, so it doesn't do anything. Now, can anybody of you see what this circuit just did? This is actually not a completely random circuit. So you want to think binary again. So let me give you a hint. So this state is, if I write this number as a binary number, is 3, right? And this is the binary number 4. So what that circuit did, it actually added 1 to the binary number stored in these 3 qubits. Okay, so that state, what that circuit does, it goes from 0, 0, n to 0, 0, n plus 1, modulo 7. Yeah, okay. Or in general, if I now put my Q state in some superposition of all the possible integer states, it increases every one of them by a number here. Okay, so this is what this circuit does. So this is just sort of showing you a little bit of what these circuit diagrams look like. Okay, but you know, quantum computers, you know, they're kind of cool. You can sort of, in principle, program any classical operation you can do on a classical computer. You can also put on a quantum computer efficiently. So an example like what I just showed you, I could just put addition on a quantum computer in the same, also efficiently. But where it's really interesting, and this is really what Richard Feynman noticed already back in 1981, so 40 years ago, he made this statement at a conference at MIT, where he says, trying to find a computer simulation of physics seems to me to be an excellent program to follow out. And he is referring here to the use of quantum computers. The real use of these quantum computers would be with quantum mechanics. The point is, nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. And by jolly, it's a wonderful problem because it doesn't look so easy. So what Feynman is saying, if I want to simulate a quantum mechanical problem, I should actually use a quantum mechanical device to simulate it. And that's essentially what we're trying to do with quantum computing. So the question then becomes, as I argued to you, well, quantum field theory is certainly a quantum mechanical problem. The question is, can we actually simulate a quantum field theory on a quantum computer? And this is an answer that was answered affirmative about 10 years ago in a really beautiful paper by John Preskill at Caltech and Keith Lee and Stephen Jordan, where they essentially prove that every ingredient in this S matrix that you have, you can put efficiently on a quantum computer. And by efficiently here, I mean that it scales logarithmic with the size of the Hilbert space. Okay, so instead of scaling linear with the size of the Hilbert space as it does on a classical computer, right? My matrices scaled like the size of my Hilbert space. So a matrix multiplication goes like the square of the Hilbert space. A quantum computer can do these operations scaling logarithmic, or powers of a logarithm of the Hilbert space. Now, of course, you all know the logarithm of a big number is a much, much, much smaller number. Okay. And so let's see what this does. So now let's say, okay, maybe I can just, why did I tell you all about simplifying the problem in the first place? Why don't we just use a quantum simulator, a quantum computer to directly simulate the LHC? So let's figure it out. Remember, the dimension of my Hilbert space was 32 raised to the power of 10 to the 14, which was a number that was essentially infinity. Well, the logarithm of that number is 5 times 10 to the 14. Now that's a lot smaller than this number. But I still need the number of qubits, order 10 to the 14. That is still huge, okay? And even if you assume that Moore's law is going to continue on quantum computers, so essentially we have twice as many qubits every year from now on, this will still not happen in any of our lifetimes. Okay, so while this is much, much, much smaller, I think it's still inconceivable to have an actual, working quantum computer with like order 10 to the 14 qubits. And this is really sort of a lower limit here in what I mean. However, what is important here to remember, and this is what I argued already previously, right? I don't actually need to simulate that whole collider environment. I don't care. It's typically, like, for example, the short distance physics, I can compute reliably using perturbation theory. The correction, if I say, look at the Higgs, the short distance process of a Higgs cross section, we now know this to n cubed LO, the uncertainties are at the percent level. So there's no real need to sort of do these short distance physics put them on a lattice. I can just use directly quantum field theory and then perturbation theory. And so what we really should do is we should it's obvious we shouldn't use these brand new emergent technology quantum computers to solve things that we already know how to solve, right? Clearly, quantum computers are lagging far behind classical computers, and they'll probably always lag behind classical computers. So we should try to find the unique problems that it can't do on a classical computer and then solve those on a quantum computer. And so this is why we sort of propose this idea of combining quantum computing with effective field theories. So the idea is that we propose in our paper is to actually not compute the full S matrix on a quantum computer, but compute these objects that sit in this factorization theory on a quantum computer. And in particular, you want to compute, say, the soft function. Now, I mentioned earlier that the soft function can be written in a way that's very similar to an S matrix, and this is just what I'm proving here. So the soft function, it's a little bit different. You start from a vacuum state, not from 2 protons, but you start from a vacuum state. And then you actually don't just do time evolution, but you actually have to put an operator in here, which are Wilson lines. And essentially what that describes is sort of these fast moving fermions, that essentially there are color sources in that these soft particles can feel. Okay, but then you go to some state. But at the end of the day, this is a very similar expression in spirit to the S matrix. And again, I have the same thing. A state is a vector in my Hilbert space. These operators are matrices in my Hilbert space. And everything I can write here is again written in terms of these fields. So it has the same underlying assumptions as the S matrix, if you want. So how does something like this look like on a lattice? So let me show you. So really what we're having, these Wilson lines are just essentially fields that move out. So this Wilson line is sort of what is called a path-ordered exponential. Doesn't really matter what it is, but it's essentially a field that sort of moves out along sort of the classical trajectory that moves at the speed of light. Okay, so if you don't, I won't explain that in a way that becomes understandable, so you just have to believe me at the moment that that's what that is. And so really what that means is, if I have a lattice and I want to simulate this operator, really what I want to simulate, I want to start in the vacuum, and I want to take sort of an excitation of this lattice point, and now I want to move it out at the speed of light. So I kind of want to start exciting field points along the lattice side here, and then I have another one, say it moves in the other direction, so it moves this way. Or that full operator that I had written down that sits in the middle of that S matrix, I start with a vacuum, and then I sort of want to move these field values out. So, if you want to understand more, you should read a paper. I'm trying not to have too many equations. I just have this one slide of equations just to prove that you can actually write this down. So you can essentially take your Wilson lines that I had before. Remember, they were written as path-ordered exponentials. And now I do what I told you before. I take my my integrals, turn them into sums. And I can now simplify this thing. And essentially, I can write this time order product that sat in that soft operator. And I can write it in a form that is sort of products of fields with sort of time evolution in between. Don't worry if you don't understand where this comes from. It's not understandable from my talk. You really have to work through the math. It's not very complicated, but you'll have to do it. But the point is, I can set this up. I can write this in terms of matrices. And what is more importantly, I can actually devise, similar to what Preskill showed, I can again write I can do this in a way that is still in the same way that is logarithmic with the size of my Hilbert space. Okay, so I can essentially write a quantum circuit here which scales like the logarithmic size of my Hilbert space. And now if you remember right, that my Hilbert space was 32 raised to 10 to the 6th power. So now I'm needing something like 5,000 qubits. Now that is something I can actually hope to get in the not too distant future, right? So at the moment we have quantum computers that have sort of 100 qubits. So I think order thousands of qubits, that is something that's possible in the next maybe 5-10 years or something. So the point is, you can do something like this in sort of the maybe 10-year time scale, but we did want to actually show, and I want to leave you with this, that you can do something right now. Now, right now, the quantum computers, they're really noisy. They don't have a lot of qubits, so I can't simulate anything really realistic. So what we actually did is, we worked out all the circuits that you need for the time evolution for these Wilson line operators. We validated that you can really get, Hamiltonian evolution. So we literally, implemented the Hamiltonian and the time evolution operator on my system. And we've sort of checked. So what you can see here, that with the circuit, if you work out the circuit, you should essentially find sort of the absolute value of 1 plus the expectation value of vacuum going to vacuum with Hamiltonian evolution on it. So if you work this out, there should be sort of a cosine behavior that where the wavelength of the cosine is given by the energy of the ground state. So what we're just showing you here is that in black, the black dotted line is the exact answer. And in red is sort of the result of this quantum circuit. So just to show that this actually works. Now, as I argued, quantum computers at the moment not there to do this simulation. So we did sort of a very simple problem. We said, okay, let's put this on 3 lattice sites. This is clearly not something that gives me any phenomenologically relevant results. But I can do this procedure. So I go into 3 lattice sites. So essentially, I start at the vacuum here. And now I let my Wilson line just hop once to the next lattice point. And at each lattice site, I use 1-bit, 2-bit, and 3-bit digitizations. Actually, 2-bit is what we use at the end of the day. So at the end of the day, this system sort of fits on 3, 6, and 9 qubits. And those I have actually reasonably clean qubits available. This is just showing that actually using the small bit digitization actually works pretty well. So what I'm showing you here is actually, this is 2-bit, 3-bit, and 4-bit digitization. And what I'm showing you here is the fractional error in the first, whatever it is, 1, 2, 3, whatever, the first 15 eigenvalues of my field theory. So I'm taking my Hamiltonian, I get the eigenvalues of my Hamiltonian. I can do this exactly. And then I can check if I put digitization on and how well do I get them. You can see already with 2-bit digitization, I'm already at an error of about 1%. 3-bit digitization, I'm already at per mil level, sub per mil level accuracy. And you can actually show that this has exponential scaling. So you can really use a pretty coarse digitization, which sort of supports that I set maybe 5 qubits is perfectly fine even for the future. And so at the end of the day, here's the circuit that we worked out, and we also had an analytical result that I can work out for these for this lattice result on 3 lattice sites. And so let's actually look at some results. That's sort of the last. I have maybe 1 or 2 more minutes for some results. So if I have, so this is now, so what am I doing here? I'm doing my Wilson line, like this matrix element, the soft matrix element. So it's I start with a vacuum. I put my operator that I had in here, and I'm looking at the 2 states that I have, either going back to the vacuum state or I'm going to the first excited state in my system. And as I argued, I can actually, on 3 lattice sites, I can do this computation analytically, and that's the analytical result for the ground state. So the ground state going to the ground state going to the first excited state as a function of the coupling constant. So it does make sense if I have no couplings in my theory at all, and these Wilson line operators, these y's are actually e to there's a g in the exponent. So if g goes to 0, then all these Wilson lines become identity operators. So essentially nothing happens. So I should just go perfectly back to the vacuum. But if I increase g, essentially I can start radiating particles out, so I can go into some excited state. So this is the analytical result. This is the result if I do 1-bit digitization on my quantum circuits. This is the result if I do 2-bit digitization. That's the result if I do 3-bit digitization. Now, this is simulation. This is not an actual quantum computer yet. This is a simulation of the quantum circuit, but it shows how well the quantum circuit can actually push this result. Now let's actually run it on a real quantum device. So we went onto the quantum devices that IBM has available, that we have access to. And there is one other thing that I wanted to do, because on an actual quantum computer, to be fair, it is actually hard to prepare that exact ground state of my field theory. So we actually prepared a ground state that is close to the exact ground state, but is essentially, again, is correct in the 2-bit digitization that I was using on my quantum computer. So that's why my exact result is now a little bit off the analytical result, because I'm not working with the exact ground state. But now let's try to see how an actual quantum computer, so this is the simulation of the circuit. So I now want to see if a quantum computer can reproduce this result. So if you run a quantum computer, you put the same circuit that gave me this result on a simulator, on a quantum computer, you get this. So, it has the same shape. Maybe you say, that's success, but there's a pretty big difference. In particular, even if I have 0 coupling, and I should say I didn't run it with 0 coupling, I run it with like 10 to the minus 4, or some tiny coupling, such that the quantum circuit doesn't actually get that the compiler doesn't simplify it down to an identity operation. But even then, I actually don't get 1 back out, I get 0.8. So what is going on? Why is the quantum computer not reproducing the simulation? Well, that you can all track down the noise. There's lots of noise in the quantum system. For example, you can imagine, even if you put a qubit into an excited state and you wait a while, that excited state might just spontaneously decay back down to the ground state. So even if you put a qubit into 1 state and you measure it out later, you might actually measure it in a 0 state because it can decay. So that is called a measurement error quite often. And that's what's happening here. And then second, these gates, I'm trying to put these gates on, and these gates are essentially telling some system to rotate, say take a system from a ground state to an excited state, maybe through some laser pulses or microwave pulses in these in condensed superconducting quantum computers. And these have errors, right? Typically these are sort of a few % errors, but every one of these 2 qubit gates actually has about a 1% error. And these circuits have sort of over 20, 30 gates in them. So it's not surprising that at the end of the day, I have a 20% error on my system. But we can actually, there's known techniques that we've also developed in my group, how to correct or mitigate some of these errors. And you can do that directly on a quantum system. So let's try to be as aggressive as we can to mitigate these errors. And I'm not using that I know the result. Okay, I'm really just using the quantum computer itself. And if I do the best I can at mitigating these results, I'm getting this result. So that result, I think, looks pretty encouraging. That result is very close to this yellow exact line. And, you know, as I said, the main reason it's not on the blue line is because it's actually the yellow line isn't on the blue line. So if I were to actually be able to use 3-bit digitization, which would essentially make this yellow line lie on top of that blue line, I suspect my quantum computer could do that too. But the problem is now that also requires a lot more gates. So I think the fidelity of the current quantum systems are probably just not good enough to run this with 3-bit digitization. So this is where I want to leave you with. So essentially, what I've shown you here is that you can sort of really go about really simulating a quantum field theory from first principles by taking the quantum field theory problem, turning the quantum mechanics problem. And essentially by combining effective theories with quantum computers, the effective theories making the overall size of that Hilbert space significantly smaller by many orders of magnitude, and then combining it with a quantum computer, which essentially takes the size of the Hilbert space and makes it and depends it on logarithmically on the size of that Hilbert space. I think we have the possibility to really compute long distance effects in collider physics from first principles. And please note, there was no perturbation theory to this. This was fully non-perturbative calculation of this effect. Now, what this work has shown that, you know, you can set this up and, you know, current machines can do sort of really simplistic problems. There's many things that we really need to do before this actually becomes feasible and relevant for collider physics. First of all, I didn't really mention this, but my entire calculation here was done with scalar field theory, not with gauge theories. Clearly, we want to describe SV3 in the end, so I need to deal with an SV3 gauge theory, not a scalar theory. I've only computed here the simplest overlaps. I only did vacuum to vacuum, vacuum to first transition. So we should work on much more general state preparations that I can do. And then, of course, another thing that I didn't even mention here, that once I put things onto a lattice, I'm actually putting infrared and ultraviolet regulators into my theory. You actually have to be careful about renormalization. So I just work with bare couplings here. That is not quite right. You actually have to carefully think about the renormalization of your lattice field theory. 1 and 2 are things that we're actually very actively working on. We're actually, this is something, you know, more general state preparation. We're actually just finishing up the paper on. I'm working right now with a postdoc at CERN on trying to do this in a U1 gauge theories. It's still not SV3, but you know we're getting there. It's a gauge theory at least. And this is something that we're sort of starting to think about, but of course it's very important. So lots of things that still need to be done, but I think also very exciting progress and you know, very exciting prospects. So I want to leave it here and ask for questions. I'm sorry for going over time.
Are there any questions?
Yeah, I have one. So this first of all, this was really an interesting talk, quite exciting to see what's possible now and where this is heading. But you mentioned the example of having the Wilson line propagate just to the next space point. So you had a world with just 3 points, and your derivative needs, or the second derivative needs 3 points to get a curvature. So aren't you running into problems with hitting the edge of the universe?
Of course. I mean, this, you should not, this 3 lattice simulation, you know, has nothing to do. I mean, there's actually all sorts of issues that we find. So if we were to compare this result, which is the 3 lattice, so this is an analytical 3 lattice result, you would compare this with the actual, you know, perturbative result, the continuum perturbative result, it would look nothing like it. Okay, so, you know, what you really want to do, like in any lattice calculation, I want to do this at many lattice points and try to do continuum extrapolation. At the moment, I'm just not able to do anything past 3 lattice points. So you're absolutely right. This is a proof of principle calculation, nothing more. But you know, the formalism that we set up, I have my code exists for higher lattice points. I can do the simulation principle, even though I always have to remember the simulation runs on a classical computer, and since the classical computer does not have the advantage of being logarithmic in my Hilbert space. I mean, the classical simulation of my quantum computer is matrix multiplication. And very quickly, I'm running out of, I'm hitting that exponential bounds. If I could simulate, of course, then I could use my supercomputers to do this calculation. So I can probably do 5 lattice points on a simulation, but then I'm very quickly running out of steam on the classical computer too.
All right, yeah.
So you're absolutely right. So, in particular, as you exactly said, right? I mean, 3 lattice point, that is really the absolute bare minimum. And actually, one thing I should mention that actually made this much simpler. So, what I show, so, let's actually do this. Where's my thing, right? So, oops, on the 3 lattice side, right? So what I said, I'm starting from here and I'm hopping once from here to here. And so what that means, this field is evaluated at one point in time. And then, of course, this field gets activated, because this field moves out at the speed of light, right? So this field essentially reaches this point a little bit later, namely the time it takes light to travel from here to here. So I need to do Hamiltonian evolution between these 2 lattice sites, right? That's essentially what this equation. Oops, sorry. What? Well, where is it? Where is it? This equation here is saying I need to evaluate this sort of at 1 lattice point. Then I do some time evolution that is just the lattice spacing apart, and then I do the next lattice point and so on. And actually in this problem, which I glossed over, essentially because I'm ending here, this time evolution immediately acts on the final state and it just gives an overall pure phase. So I actually didn't even need to do any time evolution in this simplified problem. That is only true with 3 lattice points. So, absolutely 3 lattice points, a lot of things simplified dramatically. And things will get harder at more lattice points, but that's the best we could do at the moment.
I have a question.
Yeah.
And hopefully nobody takes this the wrong way, but so like in that, so at what point do we just give up on quantum computing? Is that in 10 years after so much money's being spent? And
well, I mean, I think, so far I would argue there is, I find this works. So far the experimental situation is really very rapidly progressing, right? The amazing thing is actually when we had a paper back in 2019 where we ran a simulation on a quantum computer, and we actually got a referee report back and saying, look, this is at the end of the day, we essentially did 2 calculations. We want to show there's some interference effect that the quantum computer can model efficiently. And when we ran it on an actual quantum computer, you couldn't see a difference. So when we ran it essentially with the interference turned on and off, the quantum computer just looked the same. Okay, and then the referee came back to us and said, look, we can't really publish this paper because you're not actually showing there's any quantum advantage, because if you want it on a quantum computer, you can't actually resolve it. And then and that was, that referee report came a few months after we wrote the paper. And then we actually just ran on a quantum computer, the same IBM, well, it's not the same computer, at that point, the best computer that we had. And all of a sudden, it just looked way different. We could actually resolve the quantum interference. And then we essentially went back to the referee and said, actually, in the last few months, the quantum computers have gotten so much better. Now all of a sudden you see it. So this is proof that really this wasn't an effect of our approach. It was really just the experimental thing. So I think these things happen remarkably fast. So I would say if we can find, so for me, what is really exciting here, that there is really a proof that we can do something. Well, we know that we can do something here on a quantum computer with logarithmic resources. Of course, there is no actual proof that the classical computation cannot be done logarithmically, but we don't know any algorithm to do that. So I think given that we have these algorithms, right, and that given that I'm telling you here, for something like this, we need over thousands of qubits. I mean, this is not inconceivable. We won't be there in 5 years. We probably won't have I don't know how long it takes, but at the moment there is no indication that we won't get there, right? The progress is steadily moving. And so, to me, this looks like quantum computing now, to me, looks kind of like, lattice field theory in the 70s, right? the first lattice calculation, I think it was Kreutz who did that calculation. He did some like a single plaquette operator on 4 lattice sites, right? And that was hailed as a tremendous success in lattice QCD. And, it's taken, I mean, we still argue now about the BMW G-2 result, right? Of the BMW calculation. That's like 40, 50 years after lattice QCD came, and we're still arguing if lattice is reliable enough to be really relevant, right? And so I think we have to view it in the same way. So we are sort of in the 70s now with quantum computing. And yeah, it could be that, at some point we really hit an exponential wall. I mean, what is important is that the size of my quantum computers get bigger and that the errors get smaller, because what we really have to get to is what is called fault-tolerant quantum computing. And that requires that the errors on quantum gates go below a certain value. Now, at this point, it continues to get smaller, but if at some point we really hit a plateau and maybe we could prove that we could never reach that accuracy, well, then we might worry about whether we get there. But I see no indication at the moment that we're hitting any wall on this yet. How long it takes, of course, harder to say.
Yeah, I do. Like I said, I do apologize for the question. Obviously, always people ask those questions, and I think it's absolutely interesting that you can. I mean, you're starting with 3, but it's like eventually. I mean, like you say, the dream is to do that. Well, you won't be able to do the full scattering matrix, like you say, but if you've broken it up in very clever fashion there, and I'm just curious, like what could you use this for like early universe studies or something? I don't know, like.
I mean, there's lots of course, there's people who study like quantum gravity. I mean, people try to simulate quantum gravity on quantum computers, right? I mean, that's sort of the same thing. I can write down, if you can come up with an efficient implementation, that is not a guarantee, by the way, right? There's no guarantee that a problem you can simulate on a quantum computer with logarithmic resources. It is certainly, you can certainly prove that there are problems that cannot be done with logarithmic resources. So I think what really has happened, there's of course the famous factorizing algorithm of Shor, right? That you can do something that at least we don't know or we believe we can not do efficiently classically. But I think the more, and we've really seen a lot of this research happening in the last few years, that more and more people come up with more and more things in science that we can do. Quantum chemistry is something where really they've shown how you can simulate molecules, and I think that is just incredibly important for chemical companies, BASF, like any of these companies that make sort of advanced molecules using chemistry. Is incredibly important for them to be able to simulate these molecules, because they're wasting an enormous amount of time, making something, testing it out. And if you could simulate this, it would really revolutionize chemistry. So this is, I think, why you see a lot of industry actually putting a lot of money into quantum computing as well. My interest is obviously in the high energy physics side.
Are there any other questions?
Yeah, I had one. Maybe I missed something in the beginning, but it's just a question of the setup. How I mean, in quantum field theory, it's usually you quantize the fields, and then you promote them to operators and introduce commutation or anti-commutation relations and go from there. I kind of missed where the quantum mechanics went in your setup.
So essentially,
maybe I don't understand effective field theories well enough.
Yeah. So for example, so let me go to, I think I had my, where was my Hamiltonian of my field? Here. Okay. So look at this Hamiltonian here that I said. So on a lattice, I can write this Hamiltonian down. And now essentially these objects here, phi, and these are operators, okay?
They are operators.
On a Hilbert space. And then, for example, phi dot is the conjugate operator to phi. So you have, so the commutation relations are now that phi at one lattice point commutes with phi at another lattice point, but that phi and phi dot on the same lattice point satisfy conjugate commutation relations of phi,
Okay.
commutator phi with phi dot is I or minus I, or something like this. So that's essentially where the quantum mechanics comes in. So essentially, so really, if you look at this problem, it looks like a harmonic oscillator. You know, you have essentially, if you look at this problem, you could turn this into at each lattice site, you sort of have a harmonic oscillator. So it's a tensor product of many harmonic oscillators. That's essentially this problem becomes.
So are you somehow close to lattice gauge theory here? Or
Yes, absolutely. This is nothing. I mean, at the end of the day, what we're doing is exactly like lattice gauge theory. Well, sorry. Lattice gauge theory, typically what it does, it's what we do nowadays, it's all in Euclidean time, right? And so we don't actually do real-time dynamics. We sort of just, take an average of gauge configuration. So what this is something that Kogan and Susskind actually worked out all the way back in the 70s, which is a Hamiltonian formulation of, so lattice formulation of Hamiltonian dynamics. So really what I'm doing is I'm discretizing space, but not time. And I'm really working in Minkowskian space by essentially having a time evolution operator. But yeah, it's, other than that, I'm doing nothing but like gauge theory. So if I want to go do a gauge theory, I don't just have fields sitting at lattice points, but at lattice links. I need to worry about plaquette operators, everything that we know from lattice field theory applies here. But there's a lot of people nowadays working, how can you write sort of the Hamiltonians and lattice field theory in a way that makes them easy to put sort of on these kinds of devices. And particularly one systems where that sort of make Gauss's law, they're easy to represent. So it's all about finding the right basis, if you want, for your Hilbert space. I don't know if that answers your question.
Thanks.
I have another question. Sorry. So you had mentioned that it's really good to have a quantum mechanical problem to solve for using quantum computers. Has anybody put any thought of, so let's say you're talking about classical electromagnetism, which is really, could be formulated in terms of a quantum field theory, right? It's just, you're just taking some limits, I guess my thought there is like, since that's the case, you could, you solve the quantum field theory problem, and then could you somehow, I guess then you could eventually then calculate, basically everything we do in a classical electromagnetism out of that quantum field theory that you ran on the quantum computer. And I'm just wondering if that was or something that somebody thought about, because it's always kind of interesting, like, are there like new ways to calculate, say, electric and magnetic fields, for very, very complicated distributions and using different techniques? So
yeah, I would say there's, in principle, yes. So certainly one of the things that I'm working on at the moment is to actually put a U1 gauge theory, formulated in a way that works. But to be honest, I think there is sort of the jury is still out and what is the best way to do it. So it is a much more complicated problem than just a scalar field theory, just because, as I said, there's no lattice links, plaquette operators, and sort of all the circuits are much more complicated. And so I would say there's no sort of universally, the best way or the obvious, there's no textbook way to do even a U1 gauge theory. That's a very active field of research at the moment. But yes, in principle, it would be very interesting to do that. Now, it's actually quite interesting that it's sort of well known that if you put a gauge theory on a lattice, you actually get all sorts of new phases of matter. So, for example, if you go into really a small coupling, it's sort of a magnetic Hamiltonian, and then there is flux tubes start to develop. So even like QED on a quantum computer, so at finite lattice spacing, actually has a very different behavior than sort of the continuum QED. So, one has to extrapolate. But yes, people are certainly working on QED, and I find that's very fascinating. The fact that we don't really know how to do QED yet properly, and literally from a field theory perspective, right? This is like, how do you what is the best way to formulate? Because there's many different ways you could put a quantum field theory on a lattice, because you just have to get you want to get it right up to corrections in the lattice spacing, right? So there's many different ways to do that. and finding the optimal way. There's no, there's many different ways, and people, argue about.
I mean, can I throw something out there? Yeah. So you're digitizing space-time, but what if or space? But what if that coordinate system is not the appropriate thing to digitize, and really, maybe there's some sort of coordinate transformation one could use, and then you digitize those on that space. I don't know. That's just an idea. So
yeah, absolutely. It's not, for example, it's not clear that you want to, discretize in all the same direction. So let me give you actually an example of one thing that I did think about. We haven't worked it out yet, but sorry, this is not the animations. I want to go to my slide with a here. All right. So remember, I told you that here, sort of really the dynamics is sort of the field propagates. So, if I have two jets that move in sort of the back-to-back direction along the z-axis, then something is happening in this direction, but nothing happening in the transverse direction, right? So it's not clear at all that I really want to have the same lattice spacing in the z direction as in the x and y direction, for example, right? I might be very, very good to have maybe finer lattice spacing in this direction and more coarse in this direction. I think that sort of goes in the direction that you were saying, or if I were something radially symmetric, maybe I want to be really coarse in the phi and theta direction and sort of fine in the radial direction. Absolutely. I don't think that many people have thought about that, to be honest with you. I think everything that I have seen so far is sort of just putting it sort of statically on a sort of a square lattice, but that's clearly something that could be interesting. And I personally haven't, beyond what I just told you, I haven't thought about it. So,
yeah, I guess what you could imagine a lattice that is curved or something, and some
absolutely, yeah.
very.
I mean, you could have a completely different. You're gonna, yeah, as you said, a coordinate transformation that is much more suitable to your problem. Yeah, I mean, it could be that's just my ignorance that I don't know of the work of people. So it might be that people have thought about it, but I don't know of it.
Well, I will certainly look it up because it sounds like an interesting idea. Like you define a metric tensor or something in your lattice, and then you can define distances that way, and then maybe that can encode some structure or something.
Yeah, and you kind of want to, I guess you want to come up with a problem where it's very obvious that there is sort of that space is not sort of isotropic, right? That there's something about your problem that is far from isotropic. And you want to exploit that essentially that's what you want to exploit, that your system is breaking that symmetry, right, of space. Yeah, it's a very interesting thought. I haven't, I would, yeah. If you think of something, let me know. I'm really curious now.
Well, this was really interesting discussion. We are coming up on 3:30, and I think more and more people will have to leave. So before that happens, I want to thank you one more time for a really nice presentation and a really fitting nice end to the spring seminar series here at Wichita State. So thank you.
Thanks for hosting me. I love that. A lot of fun.